All right, these are notes for 5.6 on AP Calculus AB, solving differential equations. This is your third set of notes on solving differential equations. So we covered a little bit in Objective 3, and we did a little bit more in Objective 5. So this set of notes is going to get into some second derivatives, solving those differential equations. There's initial conditions here, and just some other various things. So we have 4 examples we're going to work through in this set of notes. The first problem says if y equals 0 when x is 1 and dy dx equals 2x plus 1, find y when x equals negative 3. So we're going to start with our differential equation, dy dx equals 2x plus 1, and find y. The initial condition they gave us, y equals 0 when x is 1, is going to tell us the constant of integration. So I'm going to start here. This is 1, 0, and I'll use that coordinate pair to find c. We're going to take our differential equation and separate our variables here. So we'll leave dy and we'll multiply dx over to the right and then integrate. So here we have y is equal to x squared plus x plus c. It's at this step that we'll use our initial condition 1, 0 to solve for that constant. So 0 is equal to 1 plus c, and c then is negative 2. So we'll plug that in here. So we have our function y, and now we can find the value of y when x is negative 3. All right, so we end up with 4. Okay. Number 2 says solve for y such that it passes through the point 3,7 and the tangent line to the graph of y at any point has slope x squared. So we're going to start right there with the slope of the tangent line is x squared. So anytime we have our slope of the tangent line, we're talking about the value of the derivative. So here we'll have dy dx is equal to x squared. We'll separate our variables by multiplying dx over to the right, and now we'll integrate each side. So y is x cubed over 3 plus c. The initial condition given in this problem is 3, 7, so this is a point contained here, and we'll plug those values in to find the value of c. So I have 7 is equal to 3 cubed divided by 3 plus c, and c is negative 2. So we'll plug that back in over here for the value of c and write our equation. All right, so now that we have our equation, we have our answer. This is all that it asked for. Find the value of y, which passes through this point, starting with this derivative. All right, the last 2 problems are going to be a little bit different. We're going to start here with second derivatives, and we are solving for the original function y. This one says y passes through 0, 4 with a slope of 2. So a couple things going on here. So like the previous problems giving us a point that we pass through. This is a point that y passes through. We're told though that at that point we have a slope of 2. That is, the function has a slope of 2 and the tangent line's slope is 2. So it's both things happening here. And the reason we know this is because it's happening at a point. So slope at a point is your tangent line slope, which is also your derivative. So we're talking about the first derivative. We're starting with the second derivative. So I'm going to take my equation here of the second derivative. We're going to add on a dx and integrate. So the left side is just integrating the name, the second derivative. We integrate back to dy dx. On the right side, we're going to integrate to 2x squared plus c. So this is my derivative. My tangent line slope, this is my derivative, is 2 at the point 0, 4, when x is 0 and y is 4. So I actually want to use the slope 2 for dy dx. And our x value at that time will be 0. Using those values, we have 2 equals 0 plus c. So c is 2. We'll plug that back in here and write our first derivatives equation. So I have now dy dx equals 2x squared plus 2. And to integrate back to y, we'll separate our variables. And then we can integrate again. So we have y is equal to 2x cubed over 3 plus 2x plus c. So now in initial condition, we're told that y also passes through the point 0, 4. This is x and y. So when x is 0, y is 4. So we'll plug in these values. We have then 4 is equal to 0 plus c, and so this constant is 4. So you'll notice there were two different constants. There was the constant of my first derivative, and now there's the constant of my original function. They each had a different value. That happens. They could have different values, same values. It's just the constant for each term, and you solve for it as you go. So now that I have this value, I can write my final answer just by plugging it back in. For c here, y is equal to 2x cubed over 3 plus 2x and then plus 4. The last example we have, number 4, is very similar, but instead of telling us a slope at a point, we're just given 2 initial conditions, basically. So this can be tricky. A lot of people assume that because it's slope, you can calculate slope through 2 points. And I'll take this moment to remind you that slope through 2 points is not slope of a tangent line. Slope through 2 points is slope of a secant line. And although it might be very close to the slope of the tangent line, they are not the same. So do not calculate slope through the 2 points. So the way we're going to do this one, we're going to add on our dx here on the right. And then we're ready to integrate, at least back to our first derivative. So dy dx on the left. On the right, x squared minus x cubed plus x plus c. Now, I don't have enough information to tell me anything about the slope of my tangent line, my dy dx here, in order to use either coordinate pair. So what this tells me is that I actually have to integrate again back to my original function before I can use this. So we're going to add in our integrals again after let's separate our variable here now. So this is y is equal to x cubed over 3 minus x to the 4th over 4 plus x squared over 2 plus, now this c is a constant. When I integrate a constant with respect to x, imagine if this were the number 5. Integrating 5 with respect to x would get us a 5x. Since we don't know the value of c, we simply get cx. But then I get another constant. I get the constant for my original function. I don't want to call it c because I'm already using c for a different constant. So maybe I'll just call it d. So this is my new constant, or the constant of my original function, where c is the constant of my derivative. So I have to find both values, and all I have are these 2 points. So the first point we're going to use is 0, 0, because 0 is always so nice to get rid of stuff. So I'm going to use this one first and plug it in here. So y is 0 when x is 0. So I have 0 is equal to all of these 0 terms plus d. And so I'm left with that value of d here is equal to 0. So I can rewrite my equation with that d value of 0 plugged in. And then we'll use our second coordinate pair, 1, 1, and plug that in to solve for c. So I have 1 equals 1/3 minus 1/4 plus 1/2 plus c. So a little work with fractions. We need a common denominator. Which is going to be 12. So 4/12 minus 3/12 plus 6/12 is going to give us 7/12. And I have 1 equals 7/12 plus c. Subtracting 7/12 from 1 gives me a c value of 5/12. And I can plug that in here to finish the problem. And there's the answer.